You know, we talked about this in Chem 1. Check out my Chem 1 playlist for solutions, talking about solvent and solute for more information. But let's just, in case you forgot about some stuff, right, we're going to go over it here. Okay, so a solution, right, has two components. You got a solvent and you got a solute. Okay, so the solvent is basically the majority of it, but it's also doing the dissolving. Okay, so your solvent is doing the dissolving. The solute, okay, is the minority component, so that's the thing that's getting dissolved. Okay, those are the two components to every single solution. All right, you're going to have some solvent and a solute. Okay, now solutions, right, we're going to relate this now back to some intermolecular forces, right? That's been one of the big things in this unit is intermolecular forces. So particles of a solute will interact with particles of the solvent through intermolecular forces, right? Bam. We just added another layer. We thought we knew everything we knew about solutions, but coming to find out, we actually have intermolecular forces playing a role in that as well. Okay. So let's go over here to some types of solutions, you know, that we've been exposed to. We got mixture. So mixture is basically your composition is going to be variable, right? And you're probably going to have two or more different substances in there. Solution, okay. In this case, if I'm talking about a solution, I'm talking about a homogeneous mixture. So these are going to appear to be one whole thing, right? And then we have an aqueous solution. Aqueous solution is basically your solvent is your water. Okay, so basically we know that water is a universal solvent. So, you know, that's the reason why they get this special solution, aqueous solution. So to distinguish those aqueous solutions, we use that AQ. And then lastly, another type of solution we have is alloys. So these are solid solutions of one metal dissolved in another. Okay, so these are your alloys. Now let's look down here at some, you know, examples. Like gas solutions. There are gas solutions where your solute and your solvent are in the gas phase. Good example of gas solutions are air, right? You know, the air is comprised of oxygen, nitrogen, right, and some other stuff. Okay. So good example of solution. Another solution, liquid solutions, right? You got club soda, you know, that's carbon dioxide and water. Vodka, you know what I'm saying? You got that liquid, solute, and solvent, right? Liquid solution. So ethanol and water for vodka. Put that vodka in that club soda. You know, now you got a whole nice little liquid solution mixture going on there. Okay. And then, you know, we also got another liquid solution. Say, you know, the most common one. One of the common ones, of course, solid is your solute. You know, that's what's being dissolved. Your solvent is a liquid. So, for instance, if we got salt, put in some water, you know, seawater, you know, salty water. So that whole deal. And then lastly, we have solid solutions. This is where our solute and our solvent are both solids. Good example of this are all alloys, but brass. Okay, if you didn't know about brass is not an element. Brass is a mixture of copper and zinc. Okay, so this is an actual alloy, that solid solution, basically. Alloys are solid solutions. A solution is when we got our solute being dissolved in a solvent. Okay, so if that is the case, then it's going to be soluble. Okay. And, you know, if you think back, right, that whole deal with the concentration, right, we have to think about that with one being, you know, if you have a dilute solution, you know, it's not as concentrated. If you have a concentrated solution, you know, you have a lot of solute in there. So remember those kind of things, everybody. Right, one example is like salt is soluble in water. That's an example of a soluble solution, right? We also have, what are things called when they can't necessarily be dissolved? That's called, we call this insolubility, right? So it's insoluble, where the substance is not going to be dissolved in that given solvent. A good example of that is oil and water. If you guys ever try to mix those two, oil's not going to dissolve in water at all. It's just going to do a layer effect. Okay. Now, talking about this handy dandy chart here, when we're talking about solutions, there's some spontaneous mixing going on. Okay. So basically, this is where, for instance, if we look down here, right, we got a concentration difference. Okay, so this is what I was talking about before, understanding those different concentrations, especially with liquids. But if we got a barrier, let's say we got one side that has pure H2O, so pure water, and then we got the other side that has that salt water in there, right? So it's that solution is on this side. Now, if we remove this barrier, we're going to see that this barrier is going to it's going to be mixing together, okay? To where it's going to mix together to produce a uniform concentration, okay? So now, right, this entire solution is mixed with pure water and this salt solution. So it just looks all like one thing, okay? It looks like a uniform solution here. All right, so solutions. We're still talking about solutions, okay? So now let's look at a gas solution, right? Before we looked at that liquid solution, now we're going to look at a gas solution. And the same thing kind of applies here, but I just wanted to focus more on the gas solution side of things. Okay, so say for instance, we got neon and argon. Okay, once again, same concept. They're separated. Okay, so I got neon gas on this side, argon gas on this side, and then I got my barrier in the middle. Okay, and both these gases are not interacting with each other. Okay, but bam, say once again, like we did with the liquid solution, say we remove this barrier. Okay, and guess what's happening? They're going to spontaneously mix together, right, to do that uniform solution, okay, which we see here. Now, this entire process, right, we actually call this process ideal solution. Okay, so this is an ideal solution when we mix this neon and argon together, or even with the salt solution. That was an ideal solution. Now, what exactly is an ideal solution? Well, basically, right, this is when our solute and solvent species, okay, in these solutions, right, basically there's not that much difference between the two. Okay, put it as simple as that. Okay. So because of this, right, these similar things, right, their intermolecular forces and attractions are very similar. So when they come together to mix together, right, it's easy for them. Okay, just think of it as an easy mix. Okay, so because of this easy mix, this is an ideal solution. Okay, and we see this, right, when we're mixing together neon and argon, right? Notice, right, the same group, same properties. It's going to be easy mix. It's an ideal solution going on there. Okay. Now, and this is the case, right? If we are talking about any, in this case, gases, or even if we think about the liquid solution example, right, to where we had one that was water, then one that was water with salt in it, right? It's basically the same thing. We mix them together, so it's, similar things there. Okay, so it's not that much difference compared to like oil or water, or even like something else, some other type of liquids that aren't really similar. Okay, so these are ideal solutions. These are ideal solutions. Okay, and they work once again because there's not a significant intermolecular attraction. Okay. Now I'm going to just hint at this. I'm not going to go hugely deep into this. Okay. But the gases mix because of energy of the system is lowered through the release of entropy. Okay. Entropy. I'm not even going to go over entropy because that's a whole unit that we're going to get to. Just to remind everybody, entropy is a measure of energy dispersal in a system. Okay, that's what it is. Okay, the measure of energy dispersal in a system. So, because of this, right, with this entropy, when we mix these gases together, right, we mix these things together, when gases are mixed, right, that energy of the system will be lowered through the release of entropy. So the energy of this entire system is actually being lowered, okay? But it is releasing entropy. Now let's talk about this real fast. Energy has a spontaneous drive to spread out over a large volume as it's allowed. By each gas expanding to fill the container, the gas's energy is dispersed over a larger volume. Okay, once again, break that down one more time. Energy has a spontaneous drive to spread out over a large volume as it is allowed. Basically, we know, right, with entropy energy, it likes to be spread. It likes to spread its wings. It likes to fly. Okay, it likes to be spread. Okay, I can't say enough. It likes to be spread out. Okay, it likes to be dispersed. Energy likes to be dispersed. Okay. Now, when we look at these examples, right, going back to this gas, let me read this one real fast. By each gas expanding to fill the container, the gas's energy is dispersed over a larger volume, right? And this is what we're saying here, that energy is being dispersed, right? That neon gas was dispersed over to the rest of this volume. Now, argon gas was dispersed over to the rest of this volume here, okay? And when this happens, right, the energy, right, is being lowered through the release of entropy. Okay, that's all I'm going to say about entropy for right now. I don't want you guys to really be focused on entropy with this. I want you guys just to understand that this is an ideal solution. Okay, this is an ideal solution. That's because the intermolecular forces are very similar. Okay, so it's an easy mix, easy mix.